Welcome back to NANDGAME. We are looking at the recently updated tracks page. Prior to this menu, the game was divided into a hardware section, that's everything that falls under computer here, a software section, which is everything from assembler through programming, and then everything after that from this transistor level on was considered an optional level. So that's where we are now in this transistor level. We'll be remaking some of the basic logic gates. Way back a long time ago, we made some of these logic gates using relays. A relay is just a switch, but it's mechanical. It uses an electromagnet and has moving parts, and transistors are sort of the upgraded version of that because they don't have any moving parts. CMOS stands for Complementary Metal Oxide Semiconductor Technology. You can read about how semiconductors work in Wikipedia. I won't go into that, mostly because I don't understand it that well myself. But semiconductors don't have any moving parts. So semiconductors you can make really, really small. If you think about an 8 gigabyte memory stick, that's tens of billions of semiconductors. You can never do that with relays or even vacuum tubes, which was the technology used in computers after relays. Transistors are really fundamental to how computers are built these days. So it's cool that they've included it. And so we'll start by, I guess, rebuilding NAND using transistors. So build a NAND gate from a CMOS transistor. There are two kinds, NMOS, which connect on one, and PMOS, which disconnect on one. So we can see how these work if you put both on the board. We'll turn the switch just to A, and then we'll input an always-on power. When the input is 0, NMOS is off and PMOS is on. And when the input is 1, NMOS is on and PMOS is off. Shown by the number in the little blue oval here. Okay, so some more information. 1 represents voltage and 0 represents ground. The output of a disconnected transistor is neither 0 or 1. Be careful not to shortcut the circuit by connecting voltage directly to ground. Oh, I kind of want to try that now. Maybe begin one of these junctions here and just, I guess, hook them both up. Oh, okay. Nothing too exciting happened, but fun to test it out. All right, so let's get started on building our NAND. Let's say we have a wire here. Let's just call it an electric wire with voltage in and voltage out. Let's say voltage is always going in on this end, and our output is what we want the output of NAND to be. Now let's say we have a transistor or relay or whatever kind of switch that we put right here. We'll say we put in a 0 or a ground signal, and that means power flows. If it's a 1, then power doesn't flow. So I think we can just split this into two, right? Add another wire here, and then add another transistor or switch here that does the same thing. For simplicity, we'll call this one A and this one B. And then let's build a little truth table. If A is 0, then B is 0, then power can flow both wires and get to the output. So then the output would be 1. If A is 1 and B is 0, well, the power can't get through this A wire. That's cut off, but it can still get to the B wire and go out. So that would be 1 as well. If A is 0 and B is 1, well, just the opposite. The power can't get through the B side, but it can go through the A side and be 1. And if they're both 1, well, the power can't go through either because both of our switches or transistors here cut it off. So if we look at that, it should be the same as our truth table for NAND. So we'll just build this circuit out. So what do we want to use here? NMOS or PMOS? Let's do PMOS. We're going to need 2 of them. We're going to hook up the first one to A and the second one to B, and then hook them both up to power. And that gives us basically the setup we have here, where power will flow if the input is 0. And you can see in our diagram, this is actually going to be a junction right here. So we've junctioned them together. When they're both 0, we output 1. When A is 1 and B is 0, or when A is 0 and B is 1, we output 1 as well. But there is an issue here with when they're both 1. Problem is that nothing is actually being outputted. We're actually gonna have to output ground in this situation. So what can we do? We can take 2 NMOS, hook one up to A and the other up to ground, and the other up to B. And instead of hooking that up to ground, we hook it up to the output of our first NMOS. And now you can see it only outputs 0 when both of these switches are 1, otherwise it outputs nothing. The way that works is more like just a wire. Say we're inputting 0 to the wire, and over here is our output. And then we have 2 switches, A and B, and it will only allow the 0 signal to flow when they're both closed. This is essentially AND. but we're sending a 0 signal when they're both closed. So that's what we have here. We just need to add another junction and junction these two together. There we go. Check our solution, and our level is successfully completed. We used 4 components, not counting junctions, and we got the simplest possible solution. Love seeing that. Next level, invert. We know we can build an invert using just a single NAND gate. This would have cost us 4 CMOS transistors, but is it possible to implement invert with even fewer CMOS transistors? So we want to create an invert, I guess, using less than 4 transistors. This should be pretty simple. Going back to our whiteboard here, let's take 2 wires. We'll send a 0 signal through this one and a 1 signal through this one. We'll create a transistor here, or a switch, whatever you want to think of it as. They're going to be hooked up to the same input, and we want this top one here to flow when the input is 1, and we want this bottom one to flow when the input is 0. And then we can junction these together to create our output. All right, so let's see if our design here with 2 transistors and 1 junction will work. All right, so let's put an NMOS on the board, hook up our A to the on here, and we'll stick the other one to ground, so that if we turn our A on, it outputs 0. We'll grab a PMOS and do the exact opposite, so that when our A input is off, it outputs a 1. Then we just junction those together and stick that junction to the output, and that should be the design we drew up. Let's try it. There we go, 2 components, simplest possible solution. NOR is a universal logic gate just like NAND. Using only NOR gates, any other logic gate can be built. So that's back to De Morgan's law, and here we just have to build a NOR out of our transistors. So I don't think we need our whiteboard here with this one because we've done all this before. We're stuck with this situation where the output is 1, where A and B are both 0. We've seen something very similar like that before. We'll just take 2 PMOS transistors, hook one up to A, the other up to B. Now we're going to want to output 1, so we got to hook up that to our voltage. And then we hook up our second PMOS to the output of the first one. So you can see that when they're both 0, we output 1, and then in any other situation, we get no output at all. So you can think of this as a wire coming from our voltage here all the way up to the output with just 2 switches on it. So this is exactly what we did before. So now we got to deal with these situations where everything is 0. So we'll take 2 NMOSes, hook them both up to ground, hook the first one up to A, the second one up to B, and what do you see here? When either input is 1, we get a 0 output. We'll junction them together so you can see it a little bit easier. When they're both 1, or when just one of them is 1, we get a 0 output. And when they're both 0, we get no output here. But hey, look, we do get an output of our 2 PMOS transistors. So we'll just junction those together, hook that up to our output, and check solution. 4 components used. This is the simplest possible solution. Okay, and that's transistors complete. A little more complicated than what we had to do way back when we were building just our logic gates. But the general idea is exactly the same. We just have to make sure that we're sending a 0 signal as well as a 1 signal. Okay, next time is functional completeness. See you then.